All right. So what I've done, I posted a homework number 4, chapter 7. Worked on it this morning. It's posted. It's on in Canvas in this week's Canvas. It will be due on Friday at 11:59. Now it covers everything up through section 7.5. Does not cover 7.6. So there'll be a separate homework for 7.6. Which I'll discuss with you on Wednesday. Because my goal is to complete 7.6 by Wednesday. If you've looked at the schedule, you'll know that seems like I'm one day behind, but I will catch up on Wednesday. This topic called t-distributions, I will also talk about on Wednesday, show you how to use your calculator to use t-distributions. We'll talk more about that on Wednesday. And then next Monday, we will have another quiz, which will cover chapter 7. And then we will have a review for our second test, which will be a week from Wednesday, which is the 31st, March 31st. Okay. That will cover everything we've covered since the last test, which I believe are chapters 6 and 7. All right, so it's sort of like a probability test. All right, any questions about that? So that's basically our schedule. So we have a homework, we'll have a quiz next Monday, test next Wednesday.
Professor, when did you say the homework is going to be due?
This homework will be due Friday at 11:59.
Okay.
So you have pretty much all week to get it done. The homework that will be I will give out for 7.6 will be due on Sunday evening. I want to have a deadline just before our review on Monday, so that way we can go over some of the questions. The homework, by the way, I will try to come up with videos which will review the answers to some of these homework questions that maybe you've been stumped on. I'll make sure that you see the solutions through pre-recorded video. Okay, so that's the way I'll handle that. You can always, of course, contact me if you have any questions about homework, anything like that, any questions about what I've covered in class, you can always contact me. You can always set up a short Zoom session just to answer those questions. So that's always a possibility too. All right, so today, again, we're going to go through 7.6, which is a very important section in your textbook because it deals with the normal or bell-shaped distribution, probably the most important probability distribution you're going to learn in this course. Okay, so normal distributions. And your calculator, hopefully you have it with you today, so you can watch the steps that I'll be starting to go through with you. Are certain steps in using your calculator that you need to be familiar with. All right, so what is a normal distribution? Well, it looks like this, bell-shaped, where the mean and the median are smack in the middle, and the mode too. Notice the height of the curve is where the highest height of the curve is where the mode is. So the mean, median, and the mode are all to be the same location in the middle, and it tails off both to the left and to the right in a symmetric way, right? Symmetric. So that if you drew a vertical line down the center of this curve, the left side and the right side would be mirror images of each other, which we can, of course, take advantage of when we calculate do different calculations with the normal curve. Now, there are different, there's actually an infinite number of normal distributions. Now the normal distribution is defined by two things, mean and the standard deviation. Now the mean, we're using the Greek letter mu to represent the mean because it's the mean of a population, and the small sigma, Greek letter sigma, we're using for the standard deviation. Mean and the standard deviation, all right? Those two things define any normal distribution. We'll need any other types of information to define it. All right. Okay. Anyway. All right. Now, besides an infinite number of normal distributions, why are there an infinite number? Because you can think of an infinite number of means and standard deviations. There's one in particular that's the most important one, and it's called the standard normal distribution. It has a mean of 0 and a standard deviation of 1. Okay. When your calculator calculates probabilities using the normal distribution, what your calculator does is takes whatever normal distribution you are referring to, whatever mean and standard deviation, and converts it into a standard normal curve. And then it has within its memory the probabilities for different parts of the standard normal curve. All right, so there's not an infinite number of these normal distributions stored in a calculator or in a computer. There's just one, and it's this one. So the point I'm making is that there is a way of converting any normal distribution into a corresponding standard normal. And what we're going to be using is what's called the z-score. You might be familiar with that because we did go over it before. We can take any raw score or any value for a variable and convert it into a z-score. And if you remember how do we do that? We subtract the mean from the score and divide by the standard deviation. Okay, so if we were going to plot all of those z-scores, we would get this so-called standard normal curve. All right. So let's continue. So it would be good to look at the standard normal distribution. One thing that we're going to be doing is calculating today, learning how to calculate the area under the bell-shaped curve and coming up with probabilities. Remember, with what a normal curve is, it's an example of a continuous probability distribution. And the word continuous means it's a variable where we can have an infinite number of values in between two values. In other words, we can calculate any value in between two endpoints in an interval. All right, so we're going to be using intervals and calculating the areas under the curve between two values. All right. This is the standard normal curve, by the way. It has a mean of 0, which means the median is also 0, and the mode is also at 0. And each of these numbers here represents the number of standard deviations away from the mean. So when we have a positive 1, it means we are 1 standard deviation higher than the mean. Positive 2 means 2 standard deviations higher than the mean. Negative 1 means 1 standard deviation lower than the mean. Negative 2 means 2 standard deviations lower than the mean. Okay, so that's how we interpret a standard normal curve. Now, it says here that for the most part, most of the areas under the curve come between negative 3.89 for a standard normal value and positive 3.89, almost all of it, nearly 100% of the curves between those two values. It also mentions here, and we might have shown this to you last time, that the equal sign for a continuous probability distribution is irrelevant. It doesn't matter whether we say probability of z is less than some number or the probability that z is less than or equal to some number, because the probability that z is equal to some number when the variable is continuous is equal to 0. All right, that was one of the things I brought out last time, was for a continuous random variable, the probability of the random variable equaling any value is 0. So it doesn't matter whether we say less than or equal to, or greater than or equal to. We're going to get the same exact answer. Now, for a discrete random variable, it does make a difference because it means we're including a particular value, and for a discrete random variable, we will have probabilities of x or z equal to some number that's a positive value. It's not 0. So discrete random variables like the binomial, yes, it does matter. that we use equal to or not equal to. But for the normal distribution, it does not matter. For a continuous random variable in general, it does not matter. Any questions about that? Because that's an important point to remember. All right. Now, in this book, like many other statistics books, and I don't even know why they even bother putting this in here, they should probably just put an appendix at the back of the book showing you how to read a normal distribution table. Before they had calculators, before they had Microsoft Excel, before they had computers, they had these tables. These tables were generated, and you can calculate probabilities using tables. But obviously, you have a calculator, a TI-83 or 84 calculator. You have Microsoft Excel if you need to use it. There's software out there that does this. There's apps that do it. No need for tables anymore. And yet these textbooks, they continue to show you how to use a table. So basically, the fact that this course is online, and not online, but it's remote, I'm allowing you to use software like Excel in addition to your calculator. No need to have any training on how to use these normal distribution tables. Now, if you want to learn how to use it, your book that shows you how to do it. It's pretty easy, but I'm not teaching it because it's unnecessary. It's just an additional level of complication that you don't need to know. All right, because I'm going to show you how to do all of these things that are going to be shown in the textbook using a calculator. And by the way, I teach this at community colleges too. And there's, students always tell me I'm bad at math, but I've learned how to use the calculator to do these things. So don't worry about this idea of being so-called bad in math. You don't need to know much math in this course. A little bit of geometry, like we did last time. A little bit of algebra, but certainly not much more than that. You don't need to know calculus. You don't need to know trigonometry. You don't need to know anything advanced. All right. So all of this that they're showing you in these slides here are just ways of using the table. All right. Now, remember that one of the things that is recommended, and I would continue to agree with this, that whenever you do a normal distribution problem, have some pencil and paper near you, and whenever there's a problem, make a little drawing of a curve, of a normal curve. All right. So if we're dealing with the standard normal curve, notice they call it the Z curve. That has to do with that idea of a Z-score. All right. So they use the random variable Z to represent a standard normal random variable as opposed to X. All right. So just know that's the tradition. We usually use letter Z to represent the standard normal as opposed to any other normal distribution. And the others, any other one will say X. This one will say Z. All right. So if we draw a standard normal curve and they want to know what's the probability that Z is less than negative 1.76, well, negative 1.76 is less than 0, so it's to the left over here somewhere, less than 0. And they want to know what's the area under the curve that is to the left of negative 1.76. That's really what they're asking. That's why, especially if you're a visual person, I would recommend drawing a normal curve and just finding out what they're asking for. What area are they asking for? And they're asking for the area under the left tail. We can call this the left tail here. And tail to the right, we will call the right tail. So you want to know the area under the left tail to the left of negative 1.76. Now, you can use these tables or you can use your calculator. So what we're going to do now, actually, I didn't open up the calculator, but I'll do that next. Just give me a second here. Stop sharing here, and just give me, looks like we have a chat message. Somebody has some Wi-Fi issues. That's okay, Paul. No problem. All right. So let me just figure out how, yeah, let's go here. I think I can do this. All right, I'm going to actually open up the calculator, TI-84 calculator on my computer, and then open up Zoom. There we go. All right, just takes about a minute for it to open up. All right, good. There we go. All right, let me share the screen of the calculator. So I'll clear the screen. Clear button basically clears the screen on the calculator. Now, what we're going to use today, we're going to be given values of z, or even another type of normal distribution with a different mean and standard deviation. And we're going to be asked to find the area under the curve, or the probability that's associated with that. So the way to do that is we're going to hit our second button and then the VARS button again. That's where we found the binomial PDF and binomial CDF, if you remember from last time. Notice right on the top is the normal. Now, for some reason, I'm not really totally sure why they list the normal PDF. Remember, with a continuous random variable, the probability that x is equal to some number is always equal to 0. Not sure why they have that there. There might be some special reason. So and this is something you should note, write it down, or, I mean, you'll get used to it after a while. Option 2 is the only one we're going to use for the normal to find probabilities. So it's normal CDF. Remember, CDF represents cumulative density function. It's going to find the probability that a random variable is less than or equal to, or less than some number. We're going to choose that one, normal CDF. And once again, if you have an 83 calculator, you'll have a blank screen with the word normal CDF and an open parenthesis. So you have to know the order of these, what's here. All right, so you have to learn the order. There are YouTube videos out there for 83 calculators calculating probabilities using the normal. So if you forget or something, you can always watch one of those. But just know that this is the order. So what's lower and upper mean? Lower means, again, we're going to be finding probabilities between two values. That is in an interval. So the interval, and any interval, is going to have a lower endpoint and an upper endpoint. Picture an interval along a number line. Lower endpoint, upper endpoint. We have a lower endpoint, upper endpoint. We have the mean. Notice it defaults to the standard normal because it has a mean of 0, standard deviation of 1. You can always change it if you have another type of normal distribution. But in this case, the one that we're looking at, we're going to be using the standard 0, 1, the mean 0, distribution 1. So the problem, so I tend to see what the problem was once again. Probability that z, the random variable, standard normal random variable, is less than negative 1.76. Now, one of the properties of a normal distribution, even though you can't see it on this curve here, is that the left tail continues to negative infinity. It never actually touches the x-axis. The same thing with the right tail. It continues to positive infinity and never quite touches the x-axis. So you might say, all right, what they're asking you to find here is the area to the left of negative 1.76. Well, that's the right endpoint, right? What the heck? Where is the left endpoint? Where is it? Well, there's really no left endpoint. Well, one thing that we learned just a few minutes ago is that practically the entire curve here, the standard normal curve, is almost 100% of it is between negative 3.79 or 78 and positive 3.78 or 79, whatever those numbers are. So it's very safe, actually, to pick a number for a left endpoint, which is like negative 1,000 or something like that, or negative 1,000,000, whatever. It doesn't really matter because the area to the left of negative 1,000 or negative 1,000,000 is practically 0. There's a little bit of an area there, but it's hardly anything. So what we have to do is artificially create a left endpoint, which is safe to use. In this case, negative 1,000 is much smaller than negative 1.76. And so we're going to say negative 1,000 for a left endpoint of this interval and negative 1.76 for the right endpoint of this interval. Okay, let's go back to the calculator. Now they do have something in here which is sort of like negative 1,000, but sometimes this, for whatever reason, you may replace this with another number and then it disappears. So I would get into the habit of using negative 1,000 for the left endpoint. Now, be careful. You want to use the negative symbol, which is down on the bottom here, and not the minus sign. Put the minus sign here, you're going to get an error on your calculator. I'm telling you that up front. People always, but many people make this mistake, and they wonder why they're getting an error in their calculator. Well, because you're using the minus sign. You need to use the negative button here. So I'm going to put negative, and then I'm going to type in 1,000. My lower endpoint. Now, left and lower mean the same thing. All right, lower endpoint, left endpoint, same thing. Scroll down to the next one, and remember, it was negative 1.76, I believe, right? I think that's what it was. Negative 1.76. And I'm going to leave the mean as 0, standard deviation of 1, because it is a standard normal. So we're going to scroll down and hit enter when we get down to paste. Now, again, if you have a TI-83 calculator, you're going to type it in this order. You'll have the normal CDF, open parenthesis, you'll type in a negative 1,000. Make sure you put a comma in between the 4 different values. Then you have negative 1.76 as your right endpoint. You have to do comma, 0 for the mean, comma, 1 for the standard deviation, close parentheses. Then we'll hit enter. And there it is. Now it gives you many decimal points here, as you can see. All right, there's 4, 8, there's 10 decimal places here, but normally I'll ask you to round your answer to 3 or 4 decimal places. So in this case, rounding it to 4 decimal places, it would be 0.0392. So that's the probability that the of z being less than negative 1.76. All right. So again, using your calculator, the only thing that you need to know are the steps of coming up with these answers, right? You're not doing any actual calculations. You're just putting in the right steps with your calculator. Any questions about that? Well, that's done. Okay, and remember, for finding probabilities with a normal distribution, there's only one function we're going to use, the normal CDF. That's it. We're not using anything else. We're not using the normal PDF at all. All right. So let's move this out of the way here. All right, let's go back to the PowerPoint. Okay, see, you get the same answer with a table. Now, with the table, by the way, it doesn't give you all possible areas and probabilities. There are some that it will not give because you may have the z down here might be more than 2 decimal places. It might be 3 or 4 decimal places. But your calculator gives you the precise answer. And actually, you can always test it if you wanted to. If you had an app that did the same thing, you'll notice your calculator will give very precise answers. So it's actually better than one of these tables. Another one would be z is less than 0.58. Well,
Professor, we can't see your screen.
I'm sorry. Yeah. Sorry about that. Back to the previous screen here. Yeah. Well, here you go. It gives you the same answer using one of these tables, but what I'm saying is your calculator will always give you an exact answer. This is just another example of the same type of problem. Notice that in the previous problem, it said less than negative 1.76. This happens to say less than or equal to negative 0.58. Remember, continuous probability distributions, this is going to be the same answer as z is less than 0.58. The equal sign doesn't matter with continuous random variables. And if you again, if you just typed in 0.58, let's do that with our calculator. Okay, and again, I'm going to go back, scroll down one, hit enter, and put negative 0.58. Notice it's a less than or equal to problem, or less than problem. So I'm going to keep the lower endpoint the same. Again, it's negative 0.58. Oops, right? Period. 0.58. Scroll down, hit enter. You have to hit enter again, unless you have the 83 calculator. And you get 0.28095, which, by the way, would be 0.2810, right? If you rounded it to 4 decimal places. Go back to the PowerPoint. Okay. All right. Now I put negative, didn't I? It's actually positive. Let's go back. Okay. Put negative instead of positive. Let's go back. Calculator, and let's just change the problem to positive. 0.58. All right, so we'll delete the negative there. Hit the delete button will do it. Go down, hit enter, another enter, 0.7190. Now, did you notice that the answer is the complement of the previous answer? Notice that? It should be that, shouldn't it? It should be that because of the normal curve being symmetric. So 0.28 is to the left of negative 0.58. It should also be to the right of positive 0.58. That 0.28 probability. Therefore, the area to the left of positive 0.58 must be the complement, which is 0.719. Okay? Any questions about that? All right. So it's very good that we have this calculator, right? I always tell people, never had it when I learned. Okay? Skip that. Look for another type of problem. Now they don't have a problem here with greater than, but if we did greater than, let's do a greater than problem. See if we have anything like that here before we do in between. There we go. What if we're interested in the probability that z is greater than 1.96? This one here, greater than. Okay. Let's find that probability. So it's a greater than problem. Now I'm going to clear this out. It's easier to see. Again, we're going to go to our normal CDF. Now, if it's greater than 1.96, that means we're dealing with the right tail, and the left endpoint is going to be 1.96. Now, the curve continues on to positive infinity, or to the right, so we have to pick a positive number, a large positive number for our right endpoint. Let's make it positive 1,000. Why not? I'm going to type in 1.96 here, scroll down, and put positive 1,000 for the right endpoint. I'm just picking some large number for that the right side of that interval. So I'm quite sure that the area to the right of a positive 1,000 is practically 0. If I scroll down, hit enter, I get, if it rounded to 3 decimal points, 0.025. 0.025. So the area to the right of 1.96 is, or probability, is 0.025. Now, if we were going to follow along with what the book is telling you to do, go back to the slides, it's going to ask you to say, all right, well, the table I'm using only gives me probabilities that are less than. I need to find a probability that's greater than. So I'm going to have to say 1 minus the probability that z is less than that. So you have to do this subtraction thing. Notice I didn't do that with the calculator. It was unnecessary because I drew, if I was doing this, I draw a little curve and I know 1.96 is to the right. And I want to know the probability that the area is to the right, right? That's the probability of that area on the right, that right tail. So I know the left endpoint now, or the lower endpoint is 1.96, and then I'm picking a positive 1,000. Positive million, doesn't matter, something big would be sufficient. Positive value, sufficiently big enough, and therefore I'm finding the area to the right. Okay, and I don't need to go through this calculation. So a lot of this that you're seeing in the textbook, if you do read the textbook, is avoided. A lot of these algebraic things are avoided just by using your calculator in the proper way. All right, now let's go back to that problem with in between. Suppose we wanted to find the area, the probability between two values, between negative 1.76 and 0.58. Now, if you remember from algebra, this is how you would write it, right? This is how we wrote intervals in high school. We would put the variable in the middle, and then we would have less than some number, and then on the left, it would be greater than some number, all right? This is the notation we used to use in high school. Now, according to this book, you would take the probability that z is less than the upper endpoint, subtract the probability that z is less than the lower endpoint. So you have to do the subtraction. Now, with your calculator, you don't even need to do that. You don't need to do it. Why? Because you just simply use the lower and upper endpoints in your calculator. Just plug in the numbers, and it'll give you this answer. So negative 1.76 on the left of the interval, positive 0.58 to the right of the interval. Back to the calculator. We'll do the normal CDF again. All right, so the lower is going to be negative. Remember to use this button down here, negative 1.76. The upper is going to be positive 0.58. Again, it's a z, so we leave the mean and standard deviation as 0, 1. Hit enter and hit enter again. Your answer. How about that? No subtraction needed. You just plug in the numbers. So with this calculator, you can do much of what the book is saying to do in an easier way. And there's really, if you practice enough, if you go through the examples with the procedure that I'm showing you, because these are the 3 types of normal distribution probabilities that you'll be asked to do. Probability to the left, which is less than, the probability to the right, which is greater than, or the probability in between two numbers. That's it. That's it. There's no reason to get these problems wrong. There's no reason for it unless you don't do anything, literally not pay attention or not. There's no math involved here other than knowing what the answer is, right? All right. Go back to the PowerPoint. Okay. Now, if you wanted to find the probability of z being greater than a negative number, negative 1.28, you would do the same thing that we just did. We would hit negative 1.28 as your lower endpoint, positive 1,000 as your upper endpoint, and you're going to get 8.8997 approximately. All right. Once again, this is how you do it with your calculus. Very easy. Now, in this section here, what they're doing is they are doing the problem in reverse. So we're going to hold off on that right this second. And let me see if there's anything else in here. I hope there is. So I'm just going to jump ahead a little bit here. I don't want to show you that yet. Here we go. So I'm going to jump ahead, and I want to go to slide number 24, because I want to repeat many of the things that we just did when we're given another normal distribution. Now remember, your calculator and this so-called table that they have in the textbook, if you're given a normal distribution with a mean and standard deviation other than 0 and 1, you're going to be, what the book is telling you to do is to convert it, whatever numbers that you're looking at, into a standard normal. That's what it says to do, and then do your probability calculations. Well, guess what? You don't need to do that, because your calculator does that for you. Now, you should be familiar with how it does it, because it uses the z-score formula. That is, it takes the value, the raw score you can call it, x, subtracts the mean, and divides by the standard deviation. And what you end up with is the z-score, which then you can use the standard normal for. All right. So you can learn how to do that. It's helpful to know that, but it's unnecessary to actually do the probability calculations. Let's just look at an example. Well, let's actually look at rather just look at an example here without looking at all of this arithmetic here. All right. Here's an example. And believe me, these are typically word problems, but don't be fooled by the word problem. What you're looking for is things like the normal distribution. You want to see that it's saying normal distribution or normally distributed. That would be another phrase you're going to look for. You're going to look for a mean. You're going to look for a standard deviation. And then they're going to ask you to find a probability. Now, the word probability and proportion mean the same thing. If you want to know what proportion of birth weights, it's the same as the probability. Okay? Makes sense, right? So if they give you, actually, let me just write down these numbers here. So, if we have the mean as 3,500 grams, and these are birth weights, right? And standard deviation is 600 grams. And they want to know what proportion of birth, when they're saying it's normally distributed, what proportion of birth weights are between 2,900 and 4,700. All right. So let's just go to the calculator. We'll see how easy this is. It's really, it is very little for you to do. I mean, you just have to know what to do with the calculator. Now I'll clear the screen. Once again, normal CDF is what we want. Now, in this case, we're using a different normal distribution, not the standard normal. So our lower value, they sit between 2,900 and 4,700 grams. So our lower endpoint is 2,700. Our upper endpoint is 4,700. Now we have to make sure we change the mean now, because we're dealing in original units of grams. So the mean is 3,500 grams. The standard deviation is 600 grams. You see what I did? I just plugged in the numbers. That's it. Scroll down, hit enter again. There it is. That's the proportion of birth weight between those two birth weights. The proportion of birth weights, 88.6. If you wanted to express it as a percentage, you could say something like 88.6% of all birth weights, or all births have weights between 2,900 and 4,700 grams. That's how you would interpret it. Okay. See how easy, this is very easy. It's very easy. I keep saying it's easy. I mean it, right? It doesn't matter whether you're good in math or not good in math. You should be able to follow these steps and do this. Now, in the book, they're telling you to convert the 2900 and the 4700 into z-scores. You really want to do that? Yeah, you could if you want. And then what do you have to do? Then you have to find the area in between these two z-scores. And in the book, they say subtract the two areas. I just showed you how to do it in one step. Same answer, right? 0.8185. So this book giving you the long way of doing it. Okay. One of the things that they're trying to show you here is that when you convert all the numbers into z's, you get your z curve, and now you're trying to find the area between -1z and +2z. All right, you should know this. I'm not telling you shouldn't know this. You should know this. I mean, if I gave you a problem like, what is the probability that a child selected at random has a birth weight between 2,900 grams and 2, and a weight if that's 2 standard deviations greater than the mean, you should know that 2 standard deviations greater than the mean is 4,700 grams, right? Two standard deviations, 2 times 600 is 1,200. 1,200 plus 3,500 is 4,700. So I could give you a problem like that and see if you understand that you can convert an original value into a z, and then you can go backwards, right? You can convert the z into the original value. You should be able to do that by following the arithmetic here. But in general, if they just are just giving you the original numbers, you just plug them into your calculator. All right. Here's another one. Birth weights were observed for many babies born in Canada. About 82% of them will fall between 2,900 and 4,700. Right? That's what we just found, right? What is the probability that a randomly selected baby born will have a birth rate greater than 4,500? Greater than 4,500. Now, use a calculator. Now, one of the things, if we use the normal again, it will keep the information that we put in before. It won't disappear. It stays in there, even if we shut off our calculator. We will, these numbers will remain in there until we change it. Now, what did it say? It said, what was the number again? Can somebody tell me? It was greater than what number? Was it 4,500? Was that what it was?
Yeah, 4,500.
Greater than 4,500. Now, if we drew a curve here, we would have the mean as what? 3,500, right? So the normal distribution would have a mean in the middle of 3,500. Standard deviation 600. Can you picture that? So one standard deviation greater than the mean would be 3,500 plus 600, which would be 4,100. One standard deviation less than the mean would be 2,900, 3,500 minus 600. You get the idea? Now, so greater than 4,500. So the lower, because it's a greater than problem, we want to have the lower endpoint is 4,500. Now, by the way, in this case here, would we use 1,000 for our upper endpoint, like we did for the z's? Will we do that?
No, you have to use a higher number.
No, because that 1,000 actually is a reasonable number to use in this problem here, right? Because we're in thousands. No, we want to use a number that's big enough so that the area to the right of that number would be practically 0. Well, we know that 600 is the standard deviation. I could tell you that 4 standard deviations that are higher than the mean, all right, it's going to be the area to the right is practically 0. So 4 standard deviations is 4 times 600, that's 2,400. 3,500 plus 2,400 is 5,900, right? 5,900. So if I put something like 10,000 in here as the upper, just picking a number bigger than that, 10,000, I'm going to be safe, right? Correct? That would be safe.
Yeah.
Yeah, would be safe to use. So you have to use a little judgment here. Don't just memorize, I need to put 1,000 here for right tail problem. No, if you have actual mean and standard deviations here, you have to see what you're putting in here makes sense, right? So I want, I would always pick a number at least 4 or 5 standard deviations to the right. And 4 is sufficient, that's 5,900. So I'm picking 10,000, that's sufficiently big enough. And then scroll down, hit enter. And the probability is going to be about 0.048, rounding the 3 decimal places. Let's go back to the problem. Okay. So let's go to the next screen. See there, all this stuff they're showing here. It's good to read through it. It's good to understand how they're converting from the original scores down back to the Z's, and they're converting the 4,500 to its Z-score of 1.67. Get the same answer, didn't we? Or something close to it. Something close to it. The answer with a calculator, by the way, is more exact. If there's some difference between what the book is giving and the calculator, go with the calculator, because the calculator is more exact, for sure. All right? So, the moral of the story is, if we have actual mean and standard deviation, we don't need to convert it to Z's. We just put the numbers into our calculator and just make sure we change the mean and standard deviation to the actual mean and standard deviation. And just use the same procedure as I showed you before. All right, if it's a left tail test, we want to pick a sufficiently small number for our left endpoint or lower endpoint. If we have a right tail test, we want a number sufficiently large for our upper tail, upper endpoint. And then in between is easy. We just put the numbers in between. All right, and we'll be able to find any of these probabilities. Okay, any questions about that? Now, when they're talking about extreme values, we're going to be working backwards here. I guess I could continue with this thing here, because this way we catch up a little bit today. We don't have any quizzes or anything to do. So let's go back to when we were dealing with the standard normal. Let's look at the standard normal. And they're saying identifying extreme values. Now, what does that mean? That means that we're given the probability and we're being asked to find the value. In other words, you're given the probability, we're being asked to find the value. So let's see what they're referring to here. Suppose we want to describe the values that make up the smallest 2% of the standard normal distribution. So they say smallest 2%. That means the area to the left is 2% or 0.02. So they want you to find, now be careful how we say this. They want to find the largest value of Z such that the area to the left is 2% or 0.02. That's what they're asking you to find, the biggest value of Z in this interval. So that would be the right endpoint. Okay, so that's what we're being asked to find. What is this Z here that corresponds to 2% to its left? How do we do that? Fortunately, our calculator has a function that does that sort of thing. Clear the screen. So don't you agree that when we are given the probability and we're being asked to find the value, that we're going in the opposite direction, aren't we? And what we've done before. Before we were given the value when we found the area to the left or to the right or in between. Here we're being given the area and we're being asked to find the value. So we're working in reverse or inverse. We could call it an inverse operation. And fortunately, if we go to the calculator, it has an inverse operation. It's option number 3 here. You see it? And all of your calculators, including the 83 calculator, has this option. It's called inverse normal. All right. Now, in statistics books, they get kind of fancy with it. Sometimes they call these quantiles. Like, what the heck is a quantile? Well, don't worry about that. This book doesn't seem to use that term. They use inverse normal. So we're working in reverse. So we're going to pick option number 3, and I'll show you what option 3 has. Now, again, if you have the 83 calculator, it will have inverse norm with an open parenthesis, and you just have to put in the proper 3 numbers with commas in between. Now, what's the first thing they're asking for? They're asking for the area. Now, you have to be careful here because the area they're asking for is the area to the left. Now, if it's a left tail problem where they give you the area to the left, that's fine. That's what you type in. But you have to be a little careful if they're asking for the area, if the information they're giving you is the area to the right. So you have to be a little careful. We'll get to that in a minute. But here in this case, the area to the left is 2% or 0.02. So I'm going to type in 0.02. Now, the distribution is standard normal. It is a z. So we're being asked to find that z. So the mean is going to be 0, and the standard deviation is going to be 1. And so the only thing we have to do is scroll down and hit enter. And again, if you are using an 83 calculator, you would have inverse norm with the open parentheses, and you would put in these 3 numbers with commas in between. And what you're being given here is the actual z value, in which 0.02 is the probability or area to the left. Negative 2.05 is that z value, where the probability to its left is 0.02. Does that make sense to everybody? Everybody good with that? Let me look at the chat here. Somebody's lost it. All right, forget it. But anyway, that's how it works. If the area to the left is 0.02, the z is negative 2.05. Okay, so let's stop that. So this is called inverse operation, inverse normal operation. Yes, yes. So Sonny, you have a special calculator. It's more, maybe a couple of you have this special calculator where it gives you options left, center, and right. So that makes it even easier, doesn't it? You just pick the right area. So if the area is to the left, you pick the left option. The area is in the center, pick the center option. The area to the right option. For all the rest of you, just follow the instructions I'm giving you. All right, I'm giving you the instructions without these options here because these are only for people who have that special calculator. But Sonny, I think you're okay with that, right? Because it'll make it easier for you. You just choose the right option, that's all. You just pick the right area, whether it's left tail, right tail, or in between, and then it'll give you the answer, give you the z. All right. All right, so let's go back to the book. All right. Now, let's go to the next slide here. And it gives you a way of doing it through a table. It says the z is negative 2.05. But don't worry about it. You don't have to worry at all. Now, what if you're being asked to find the area to the right, or find the z that corresponds to the largest 5% of all z values? That is the area to the right of this z. So what we're being asked to find is the smallest z that corresponds to 5% to its right, the smallest z, right? You picture there's a bunch of z's in this area here. This would be the smallest one out of all of them. So the smallest z that corresponds to the area to the right of 0.05. Now, Sonny, again, you just pick the right tail and you'll get your answer. But for the rest of you, when we use inverse normal, this is the area to the right. What is the area to the left? The area to the right of the Z is 0.05. What's the area to the left? Can anybody tell me? You must be paying attention. I hope you are paying attention, folks, because
Be 0.95.
what is it?
Is it 0.95?
0.95, exactly. 0.95. It's the complement of 0.05, isn't it? The area to the right is 0.05. The area to the left must be its complement. 1 minus 0.05, which is 0.95. Now, what's really great about this calculator is that you could do formulas even in the calculator for what you put into it. What do I mean? Let's go back. Let's clear this out. Let's do the inverse normal again, which we need to do in this case. Now, I'm gonna clear this, what's in here. Remember, the area that they're asking for here is the area to the left. Again, if you have this special calculator, you just choose right and put 0.05 and choose the option right. But most of you don't have that, and the 83 people certainly don't have that. You want the area to the left. Now, if you don't want to do the arithmetic and just say, all right, do it in your head, 1 minus 0.05 is 0.95, you can simply type in 1 minus 0.05. Just type it in as a little formula. Let the calculator do the arithmetic. Isn't that nice? You can just type it in this way. That way you don't make any math errors. And then scroll down. 1.6449 or 1.645 is the answer if you round to 3 decimal places. That's the smallest z where the area to its right is 0.05. Notice I just put it in as a formula, the area, because I know I need the area to the left here, and they're giving me the area to the right. So if I just put 1 minus the area to the right, I'm going to get the area to the left. Or if you could just do it in your head, you can put 0.95 here. That would be fine. Same thing. All right. Any questions about that? Okay. Back to the book. See if there's any others situations here where you need to find, give you areas. All right, let's go down to other normal distributions, and we're going to do the same thing as we just did here. I'm going to use the inverse normal now if they give you actual x values. Now notice here they're using this special formula here to convert a z into an x. All right. Now, that's what you would need if you were using a table. Remember, tables only have z's. So you'd find, if they gave you a probability, you'd find the z and then have to convert it to an x. This formula here, by the way, is just an algebraic equivalent to x minus mu divided by sigma is equal to z. All right, you just multiply both sides by sigma and added mu, and then you got this formula. You need to know it. It's good to know this. It would be useful to know it, but it's unnecessary to actually do the calculation. So let's look at an example here. All right. Garbage trucks entering a waste management facility are weighed, and then they offload garbage into a landfill. So you have some data about these, about the time, right? There's some sort of time measurement here. All right. What's the random variable? Total processing time for a garbage truck at the waste management facility. And that's how long are they going to wait there and then actually offload the garbage? Average time there. So the mean over the long term is 13 minutes. Standard deviation is 3.9 minutes. And they say that these times, these total processing times, are normally distributed. They say the data seems to suggest a normal distribution. Okay. So we have 13 minutes as our mean. Let's write this down. Mean is 13 minutes, and the standard deviation is 3.9 minutes. Let's see what the question is. Those we want to describe the total processing times of the trucks making up the 10% with the longest processing times, right? Now, in this industry, those are the ones who are doing a bad job, right? You want the ones that spend the least amount of time in these facilities, not the most amount of time. So these are the ones who are not doing well, and they spend the longest processing times there. And you say that the top, the 10% with the longest processing time. So that is the right tail problem. I hope you can understand that when they're talking about the longest, they're referring to the right tail. When they talk about the shortest, they talk about the left tail. Does everybody understand that? Anybody confused by that? Because this course does involve word problems, so I want to make sure that what we're referring to here is absolutely totally clear to all of you. All right, when they say 10% with the longest processing times, they're talking about the area to the right being 0.10. They want to find the smallest time that corresponds to this, the smallest time that is in this area here. That would be the smallest x. So we're going to find, again, they're giving you an area or probability, and we want to find the value corresponding to that. That means we must use inverse normal. So the area to the right, now we have to remember 0.10 here is the area to the right, and the inverse normal is asking for area to the left. All right, so I'm going to again go back to the calculator. Again, we'll do inverse normal. You have to recognize this is an inverse normal problem because they're giving you an area and you're being asked to find the value, the time that corresponds to it. In this case, time. Okay, and now inverse normal. Now, in this case here, the area to the right is 0.10. What would be the area to the left?
0.90.
0.90. So if you can do that in your head, you can just simply type in 0.90. But for those of you who want to be careful, you could just type in 1 minus 0.10, right? Because the area to the right is 0.10. That means the area to the left is 1 minus that. Right? That's the same thing as 0.90, but you can type it in that way, which I'm going to do. Now, what is the mean? Now, here's the real advantage of your calculator. You do not need to do any conversions from a z to an x. You just have to put the mean and standard deviation in here. And the mean is 13 minutes, and the standard deviation is 3.9 minutes. You just type those in. Scroll down, hit enter. And if you round this to the nearest whole number, how many minutes? What is the smallest number of minutes where you're part of that 10% group that take the longest time? What's the smallest number of minutes for that group of trucks?
18 minutes.
18 minutes, yeah. If you round it to the nearest whole number, it's 18 minutes. So 18 minutes or more would be the top 10% of processing time. You get the idea? 18 minutes or more. Okay. No questions? And understand the types of problems you'll see on a test, just like these. It's very similar to what you'll see on a test. Now they go through this all these calculations. As you can see, you didn't have to do that. You just have to have that inverse normal thing available. Okay. Now, what are they asking for here? They're giving you a different problem, right? About 10% of the garbage trucks using this facility would have a probe. All right. They use 17.992. Notice our answer is a little bit different, right? Slightly different. That's because the calculator is giving you a more precise answer. The table is not. All right. So the table is not as accurate as your calculator. Always go with your calculator. The 5% with the fastest processing times, that would be the smallest times, right? So you have to be careful in the way it's saying this. This would be the smallest 5%. What would be the largest processing time that would fall in this group of trucks, these 5% of the trucks that are fastest? Well, this would be a left tail problem, wouldn't it? Because the times would be the smallest times, right? The smallest 5% would be the fastest. Let's go back to the calculator and calculate that. Now, it'll keep the information from before, by the way, which is nice. Put on the inverse normal, again, not being asked to find those values. Now, in this case here, the smallest 5% is the area to the left, isn't it? You drew a little curve. It's the left tail. So I'm going to clear this here, and I'm actually going to type in 0.05 because it is the area to the left. And that's the only thing that's different. The mean and standard deviation are exactly the same. It's the same problem, same normal distribution. 6.585 minutes. All right, 6.585 minutes would be the largest time where of the group that are the fastest 5% of processing times. Okay. 6.585. Then we go back to our book, PowerPoint. And then they do all this math. Notice the answer is pretty close, right? Well, your calculator's better answer. 6.585 is actually more precise. This is using tables and approximations and all that sort of thing. All right, any questions? So we've jumped ahead, and now we're actually a little bit ahead. So what are we going to do on Wednesday? What we're going to do is I'm going to teach you another distribution called the T distribution. Looks very much like the normal distribution. And I'll show you how to use it with your calculator. Now, if you have an 83 calculator, when we do the inverse operation with the T, you'll notice that your calculator does not have the inverse T operation. That's one of the disadvantages that you have having the calculator. The 83 calculator is that it doesn't have this inverse operation for a T distribution. But don't worry, if you have access to a Microsoft Excel, I'll show you how to do this stuff in Microsoft Excel, which is an alternative. Now, if for some reason you have an 83 calculator and you do not have access to Microsoft Excel, then there is another option, because there's a way of putting a program onto your calculator. This is something, by the way, for doing this in person. I have a cable that runs from my calculator, and I would just plug it into your 83 calculator and give you that program. However, since we're doing this remotely, that's not going to be possible. So please, when next session, please have your 83 calculator with you. Obviously, all the rest of you with your 84s, you'll have it with you also. But it's very important for the 83 people to be in class next time and also to watch what I'm doing, because if you don't have that Microsoft Excel and you have an 83 calculator, we'll have to figure out another way for you to do these calculations. All right. So not a problem. We'll figure it out. But I want to make sure that those of you who are in that situation have a solution. All right. Any questions about anything we've done today? And in addition to doing the T distribution, I will give you some more practice from the textbook. Some practice problems we'll be doing from the textbook also next time, which will give you plenty of practice. And then, of course, you'll have a homework assignment also, which will give you additional practice. So you should all be very well prepared, at least for the normal distribution and T distribution part of the next test. All right, I hope all of you, I didn't see many videos open here. I hope you were paying attention. This is very, very, very important stuff. So if for some reason you were doing something else, please watch the video. Don't ignore these classes, because then you have to figure out how to do this stuff. And the textbook is too complicated for this, I'm telling you. Giving you a more complicated way of doing it than the way I'm showing. So please follow along. Please make sure that you are watching and working along with your calculator next time. Your test score will depend on whether you do this or not. I've been doing this for many years, and people who do not pay attention, and I'm not saying you're not, but people typically who don't pay attention do very poorly. People who pay attention do very well. There's a big gap between the very well people and the people who don't do very well. And it's typically because they're not paying, the people do very well paying attention, the people who don't are not paying attention. All right, so please, I implore you, please take advantage of these classes because I'm showing you things that are shortcuts for solving problems, making it much easier for you to do well in this course. All right, this next test should be your best scoring test out of all three of them. Should be. I typically in the past see people with 110s, 100 to 110 in the second test. But again, I've never done this remotely since the pandemic, so we'll see how things go. But make sure that you pay attention. It will be make a big difference in your grade. All right, so that's it for today. I'll shut off if you don't have any questions, I'll shut off the video recording, and then I'll see you on Wednesday, same time. Okay, have a nice day.